We're told that in 1969, humans landed on the moon. Neil Armstrong took that famous first step. Buzz Aldrin followed. The whole world watched on television. It's one of the defining moments of human history. But here's the thing. When you actually look at the physics, when you calculate the energies involved, when you analyze the technology they had available, when you consider the radiation, the temperatures, the computational power, you start to ask yourself a very uncomfortable question. How did they actually pull this off? Now, before you think I'm some conspiracy theorist, let me be clear. I'm a physicist. I work on string theory at the City University of New York. I believe in evidence. I believe in mathematics. I believe in the scientific method. And that's exactly why this question fascinates me. Because when you do the math, when you look at the engineering challenges, the moon landing seems almost impossible. Think about it. In 1969, the most powerful computer available to NASA had less computing power than your smartphone. In fact, the Apollo guidance computer had 64 kilobytes of memory. 64 kilobytes. Your smartphone has millions of times more memory than that. The entire Apollo program was navigated with less computational power than a modern calculator. And yet, somehow, they calculated trajectories to the moon with pinpoint accuracy. They navigated through space. They landed on the lunar surface. They took off again. They rendezvoused with the command module in orbit. They came back to Earth, all with a computer less powerful than the chip in your car key. Now, how is that possible? Well, let me explain something about orbital mechanics. When you're trying to get to the moon, you're not just pointing a rocket and firing. You're dealing with what we call the three-body problem. You have the Earth, you have the moon, and you have your spacecraft. Each one is pulling on the others with gravity. And the mathematics of the three-body problem are notoriously difficult. In fact, there's no exact solution to the three-body problem. You can't write down a simple equation that tells you exactly where everything will be at any given time. You have to use approximations. You have to use numerical methods. You have to run complex calculations again and again. And in 1969, they did this with 64 kilobytes of memory. Think about that for a moment. Modern scientists with supercomputers millions of times more powerful still struggle with orbital mechanics. We use massive computational resources to calculate satellite trajectories. And yet NASA, with 1,960 seconds technology, nailed it on the first try. Well, actually, not the first try. There were the Apollo 8, 9, and 10 missions that tested various components, but still, the margin for error was incredibly small. And they succeeded every single time after Apollo 13's famous accident. They brought the astronauts home safely. So the question isn't whether the moon landings happened. The question is how. How did they overcome challenges that seem almost insurmountable? Let me give you another example. Radiation. Space is filled with radiation. Cosmic rays, solar wind, radiation trapped in the Earth's magnetosphere. When you leave Earth's protective magnetic field, you're exposed to enormous amounts of radiation. Now, the Apollo spacecraft had aluminum walls. Aluminum, that's it. The command module was essentially a thin aluminum can. And the astronauts spent days in space traveling to the moon and back, protected only by this thin metal shell. Let me tell you something about radiation shielding. To effectively block high-energy cosmic rays, you need thick shielding. Lead, concrete, water-dense materials that can absorb the radiation. A few millimeters of aluminum, that's not going to do much against cosmic rays. And then there's the Van Allen radiation belts. These are zones of intense radiation surrounding Earth, discovered by James Van Allen in 1958. The belts contain high-energy protons and electrons trapped by Earth's magnetic field. And to get to the moon, you have to pass through them. Now, NASA says the astronauts passed through the Van Allen belts quickly, spending only about an hour in the most intense regions, and that the radiation dose was manageable. And you know what? The math actually supports this. If you calculate the radiation exposure for a fast transit through the belts, it comes out to something humans can survive. But here's what's interesting. In 2014, NASA released a video where one of their engineers said that we need to solve the radiation problem before we can send humans beyond low Earth orbit. He said, and I quote, "We must solve these challenges before we send people through this region of space." Wait a minute. We must solve these challenges? But we already sent people through this region of space 12 times in the Apollo program. So what's he talking about? Well, the answer is complicated. Modern safety standards are much stricter than they were in the 1,960 seconds. Today, we want to minimize radiation exposure as much as possible. In the 1,960 seconds, they were willing to accept higher risks. The astronauts knew they were being exposed to radiation. They accepted it. It was part of the job. But still, it raises an interesting question. If we did it in 1969 with primitive technology, why is it so hard now? Why are we acting like it's some unsolved problem? Let me tell you another thing that bothers me. The temperatures on the moon. During the lunar day, which lasts about 2 weeks, temperatures on the surface reach 127 degrees Celsius. That's 260 degrees Fahrenheit, hot enough to boil water. And during the lunar night, temperatures drop to minus 173 degrees Celsius. That's minus 280 Fahrenheit, cold enough to freeze carbon dioxide. Now, the Apollo astronauts landed during the lunar morning, when temperatures were relatively moderate. But still, they were dealing with extreme heat. The lunar surface was baking in direct sunlight, no atmosphere to diffuse the heat, no clouds to provide shade, just raw, intense solar radiation. And their spacesuits? They had a cooling system, yes, water-cooled garments worn under the suit. But think about the engineering challenge. You're designing a suit that has to keep a human comfortable in extreme heat, while also being flexible enough to allow movement, strong enough to maintain pressure, and light enough to be practical. And they pulled it off. The suits worked. The astronauts didn't overheat. They didn't freeze. They worked on the lunar surface for hours at a time. It's remarkable, almost too remarkable. Now, let me talk about something else. The lunar module, this was the spacecraft that actually landed on the moon. And when you look at it, it's not impressive. It looks like it was built in someone's garage. Thin metal walls, foil-like covering, spindly legs. It looks fragile. It looks primitive. And yet, this thing had to descend from lunar orbit, land on an unknown surface, then take off again and rendezvous with the command module, all with a rocket engine that had never been tested in lunar conditions. All controlled by astronauts using manual controls and that primitive computer. Think about what's involved in landing on the moon. You're descending in 1/6 gravity. Your engine is firing to slow you down. You're trying to find a safe landing spot. You have limited fuel. If you run out before you land, you crash. If you land too hard, you crash. If you land on a slope, you tip over. And they did this 6 times successfully. Every single time. Armstrong had to manually fly the Eagle to avoid a boulder field. He landed with less than 30 seconds of fuel remaining. 30 seconds, that's how close they came to disaster. And the other missions, they all landed safely. No crashes, no disasters. Every landing was successful. Now, that's either incredible skill and luck, or something else is going on. Let me give you another example. The photographs. The Apollo astronauts took thousands of photographs on the moon. Beautiful, clear, perfectly exposed photographs. And they did this with film cameras, Hasselblad cameras modified for lunar conditions. Now, think about what's involved in photography. You need the right exposure. Too much light, the image is washed out. Too little light, it's too dark. You need the right focus. You need to hold the camera steady. And the astronauts were doing this while wearing bulky spacesuits with thick gloves. They couldn't look through a viewfinder. They had cameras mounted on their chests. They were essentially shooting blind. And yet, almost every photograph is perfectly framed, perfectly exposed, perfectly focused. How professional photographers working in comfortable conditions with modern equipment would struggle to achieve that success rate. And yet astronauts in bulky suits on the moon nailed it almost every time. Now, NASA's answer is that they trained extensively. They practiced for months. They knew exactly how to set the camera for lunar conditions. And okay, that makes sense. But still, the success rate is remarkable. And then there's the film itself. Photographic film is sensitive to radiation. Cosmic rays can fog, film, create artifacts, ruin images, and yet the Apollo film survived. The images are clear, no significant radiation damage. How did they protect the film? How did they ensure it wouldn't be ruined by the intense radiation of space? These are the questions that keep me up at night. Not because I think the moon landings were faked, but because I want to understand how they actually did it, how they overcame challenges that seem almost insurmountable. You see, when I was 8 years old, I saw the Apollo missions on television. I watched Armstrong step onto the moon, and I was inspired. I thought, if we can do that, we can do anything. It sparked my interest in science. It made me want to become a physicist. And now, decades later, as I understand more about the physics, the engineering, the challenges involved, I'm even more impressed. Because what they accomplished was extraordinary, almost miraculous. But here's what really gets me. We haven't been back. It's been over 50 years since the last moon landing. We've sent robots to Mars. We've built the International Space Station. We've launched telescopes that can see to the edge of the universe. But we haven't sent humans back to the moon. Why not? If we did it in 1969 with primitive technology, it should be easy now, right? We have better computers, better materials, better rockets. So why haven't we gone back? The official answer is money. It's expensive. There's no pressing need. We can do most science with robots. And okay, those are all valid points. But still, you'd think that in 50 years, someone would have wanted to go back. China, Russia, Europe, private companies, someone would have done it by now. Unless it's harder than we think, unless the challenges are greater than we realized, unless there's something about the moon landings that we don't fully understand. Now, let me talk about the rocket equation. This is fundamental to space travel. It's called the Tsiolkovsky rocket equation, after the Russian scientist who first formulated it, and it tells you how much fuel you need to reach a certain velocity. The problem is, it's exponential. If you want to go faster, you don't just need more fuel, you need exponentially more fuel, and that fuel has mass. So you need more fuel to lift the fuel. It's a vicious cycle. To escape Earth's gravity, you need to reach about 11 kilometers per second. That's 25,000 miles per hour. And to do that, you need a rocket that's mostly fuel. The Saturn V rocket that launched the Apollo missions was 85% fuel by mass. Only 15% was the actual spacecraft and payload, and they did this in the 1,960 seconds. They built the most powerful rocket ever made. 3,000 tons of thrust, and it worked. Every single time it launched, it worked. No catastrophic failures, no explosions on the launch pad. Now, compare that to today. We're still struggling to build reliable heavy-lift rockets. SpaceX's Starship has had multiple test failures. NASA's Space Launch System is years behind schedule and billions over budget. And yet, in the 1,960 seconds, they built the Saturn V, and it worked on the first try. How? How did they achieve that level of reliability with 1,960 seconds technology? With slide rules instead of computers, with less advanced materials, with less experience? The answer, according to NASA, is that they had unlimited resources. The Apollo program cost over $25 billion in 1,960 seconds money. That's over $150 billion in today's dollars. They had the best engineers, the best facilities, the full support of the government, and they were motivated by the Cold War. They had to beat the Soviets to the moon. And okay, that makes sense. When you throw enough money and talent at a problem, you can solve it. But still, the engineering achievement is staggering. They essentially invented the technology as they went along. Fuel cells, life support systems, spacesuits, lunar rovers, all of it was brand new, and it all worked. Let me tell you about another challenge, communication. The moon is about 240,000 miles from Earth. Radio signals travel at the speed of light, which means there's about a 1.3 second delay each way. So when Mission Control talked to the astronauts, there was a 2.6 second round-trip delay. Now, that doesn't sound like much, but think about landing on the moon. You're descending. You're looking for a landing spot. Mission Control is monitoring your fuel, your altitude, your velocity. And there's a 2.6 second delay in all communications. If something goes wrong, Mission Control can't help you in real time. By the time they see the problem and send a command, it's too late. The astronauts have to make split-second decisions on their own. And they did. Armstrong manually flew the lunar module to avoid a boulder field. He had seconds to make that decision. No time to consult with Mission Control. He just did it. And it worked. That takes incredible skill, incredible training, incredible courage. And the fact that it worked is testament to the quality of the astronauts and the mission planners. But it also raises a question. How many things could have gone wrong? How many potential failures were there? And how did they avoid all of them? You see, space travel is unforgiving. There's no margin for error. A tiny leak in a spacesuit means death. A malfunction in the life support system means death. A problem with the rocket engine means death. Everything has to work perfectly every single time. And in the Apollo program, with a few exceptions like Apollo 13, everything did work. The odds of that are remarkably small. It's like flipping a coin 100 times and getting heads every single time. Possible, yes, but unlikely. Now, I'm not saying it didn't happen. I'm saying it's remarkable that it did happen. The engineering, the planning, the execution, all of it had to be perfect, and it was. Let me talk about something else that fascinates me. The flag. You've all seen the images. The American flag planted on the lunar surface. And in some of the footage, the flag appears to be waving, moving in the wind. But wait, there's no atmosphere on the moon, no air, no wind. So how can the flag be waving? Now, skeptics jump on this and say, aha, proof that it was filmed on Earth. But the explanation is actually simple. The flag had a horizontal rod at the top to keep it extended. And when the astronauts planted the pole, they twisted it back and forth to drive it into the ground. That twisting motion made the flag wave. And in the vacuum of the moon, with no air resistance, the flag kept moving for a while. It's physics, simple physics. But it looks weird because we're not used to seeing flags in a vacuum. On Earth, a flag would stop moving almost immediately because air resistance would damp the motion. But on the moon, the flag keeps oscillating. So the waving flag isn't evidence of a hoax. It's evidence that they really were in a vacuum. It's evidence that they really were on the moon. But here's what's interesting. The fact that people question this shows how counterintuitive space is, how different it is from our everyday experience. And that's exactly why the moon landings seem impossible. Because they required mastering an environment completely unlike anything on Earth. Now let me talk about the rocks. The Apollo missions brought back 842 pounds of lunar rocks and soil. These samples have been studied by scientists all over the world for over 50 years, and they're genuine. They're unlike any rocks on Earth. Lunar rocks have certain characteristics. They contain minerals that form only in the absence of water. They have tiny impact craters from micrometeorites. They have no signs of weathering because there's no weather on the moon. And they're old, really old, over 4 billion years old in some cases. Now, could these rocks have been faked? Could they have been manufactured in a laboratory? No, not with 1,960 seconds technology, not with today's technology. We can't create rocks with these characteristics. The isotope ratios, the mineral compositions, the age, all of it matches what we'd expect from the moon. So the rocks are real. They came from the moon. And the only way to get them was to go there and bring them back. But here's what's interesting. The Soviet Union also brought back lunar rocks. Using unmanned probes, the lunar program successfully returned samples from the moon 3 times, much smaller amounts than Apollo, but still, they did it robotically. So it was possible to get lunar rocks without sending humans. Does that prove Apollo was faked? No, because the Soviet Union, our greatest rival, confirmed that Apollo happened. They tracked the missions, they monitored the communications, they had every incentive to expose a hoax if it existed. And they didn't. They acknowledged that America won the space race. That's pretty strong evidence right there. If your biggest enemy, the one you're competing against, says you won, then you probably won. Now, let me talk about radiation again, because this is really important. A lot of people focus on the Van Allen belts, but there's another source of radiation in space, solar particle events. These are bursts of high energy particles from the sunday. They're unpredictable. They can happen at any time. And they're dangerous. If astronauts are caught in a solar particle event outside Earth's magnetosphere, they could receive a lethal dose of radiation. It's one of the biggest dangers of deep space travel. Now, during the Apollo program, there were no major solar particle events during the missions. The astronauts were lucky. If there had been a big solar storm, they could have been in serious trouble. But NASA monitored solar activity carefully. They had forecasts. They knew when it was safe to launch and when it wasn't. And they got lucky. The timing worked out. But think about that. They were gambling with the astronauts' lives. If a solar storm had erupted while they were on the moon, there would have been nothing they could do. The lunar module didn't have enough shielding to protect them. They would have been exposed. That's the kind of risk they were willing to take in 1969. And it worked out. But it easily could have gone the other way. So when I look at all of this, the technology, the challenges, the risks, I'm amazed that it worked. I'm amazed that we actually pulled it off. It really was an incredible achievement. But that's also why it's so hard to do again, because we understand the risks better now. We're not willing to accept the same level of danger. We want better shielding, better life support, better redundancy, and all of that makes it more expensive and more complicated. In the 1,960 seconds, they just went for it. They accepted the risks, they pushed forward, and they succeeded. Now, let me tell you something personal. When I built my particle accelerator in high school, people thought I was crazy. They said, you can't do that. You don't have the resources. You don't have the knowledge. But I did it anyway. I went to junkyards and bought parts. I wound coils of copper wire. I figured it out, and that's what NASA did with Apollo. They had a seemingly impossible goal, and they figured it out. They innovated. They improvised. They made it work. That's the American spirit. That's what we're capable of when we're motivated, when we have a clear goal and the will to achieve it. But it also shows how rare that kind of achievement is, how everything has to align, the technology, the resources, the political will, the luck, all of it has to come together at the right moment. And in 1969, it did. We went to the moon. We achieved the impossible. But here's the question I really want to explore. If we did it once, why is it so hard to do it again? What changed? What did we lose? And what does that tell us about the challenge of space exploration? Because if going to the moon was impossible with 1,960 seconds technology and is still hard with modern technology, then maybe space is more hostile, more challenging, more dangerous than we like to admit. Maybe the moon landings weren't just an engineering achievement. Maybe they were a miracle, a perfect storm of talent, resources, timing, and luck that came together once and might never come together again. Or maybe, and this is what I believe, maybe they showed us what we're capable of. Maybe they proved that humans can do the impossible when we set our minds to it. And maybe that's the real lesson. Not that it's impossible, but that it requires everything we have. And that brings me to the end of part 1. We've looked at the challenges, the radiation, the temperatures, the technology, the risks. We've seen how unlikely success was. And yet it happened. In part 2, we're going to dig deeper. We're going to look at the specific technologies that made it possible. The rocket engines, the navigation systems, the life support. We're going to understand exactly how they overcame each challenge. And we're going to explore why, despite all our modern advantages, we still haven't gone back. So we've established that the moon landings faced extraordinary challenges. Now, the next question is, and this is where things get really interesting, how exactly did they solve these problems? What specific technologies did they use? And why can't we easily replicate them today? You see, when you dig into the engineering details of the Apollo program, you find solutions that seem almost too clever, too perfectly designed. It's like they knew exactly what would work before they even tested it. And that's what fascinates me as a physicist. How did they get it right? Let me start with the most critical component, the rocket engine. Specifically, the F-1 engine that powered the first stage of the Saturn V. This engine produced 1.5 million pounds of thrust. It burned 3,000 pounds of fuel per second, 3,000 pounds every single second. That's more than a small car. And here's what's remarkable. They designed this engine in the early 1,960 seconds. They didn't have computer simulations. They didn't have advanced material science. They used slide rules and wind tunnels and physical testing, and yet they created the most powerful single-chamber rocket engine ever built. Even today, with all our computational power, we struggle to match the F-1. SpaceX's Raptor engines are impressive, but they produce about half the thrust of an F-1. And the F-1 was built 60 years ago. So how did they do it? Well, let me tell you about the development process. They tested the F-1 thousands of times. They blew up dozens of engines. They had catastrophic failures, engines exploding on the test stand. But they kept iterating, kept improving until they got it right. And when they finally got it right, it worked. 13 Saturn V launches, 13 successes, no failures. Every single F-1 engine performed exactly as designed. Now, think about the complexity here. Each F-1 engine had thousands of parts, pumps, valves, injectors, chambers. All of it had to work in perfect synchronization. The fuel and oxidizer had to mix at exactly the right ratio. The combustion had to be stable. The cooling had to prevent the engine from melting. And they achieved this with 1,960 seconds manufacturing techniques. No computer-controlled machining, no advanced quality control systems, just skilled machinists and engineers doing everything by hand. It's extraordinary, almost unbelievable. But the engines exist. You can see them in museums. You can examine them. They're real. But here's what's interesting. NASA lost the detailed manufacturing specifications for the F-1. Not the basic designs, those exist, but the specific techniques, the tricks the machinists used, the subtle adjustments they made. A lot of that knowledge was lost when the program ended and the engineers retired. So even though we have F-1 engines, even though we can study them, we can't easily build new ones. We'd have to reverse engineer them, figure out how they were made. And that's harder than you might think. This is what engineers call tacit knowledge. Knowledge that exists in people's hands and minds, not in blueprints and documents. And when those people retire or die, the knowledge goes with them. So in a very real sense, we've lost the ability to go to the moon the way we did in the 1,960 seconds. Not because the physics changed, not because it's impossible, but because we lost the institutional knowledge, the manufacturing techniques, the entire industrial infrastructure that made it possible. Now let me talk about the guidance computer. The Apollo Guidance Computer, or AGC. This was the computer that navigated the spacecraft to the moon. And as I mentioned earlier, it had 64 kilobytes of memory. That's nothing. Absolutely nothing by today's standards. But here's what's remarkable. The software was perfect, or nearly perfect. It had to be, because there was no way to update it in flight. No patches, no bug fixes. Whatever code they loaded before launch, that's what they were stuck with. And the programmers achieved this. They wrote code so efficient, so carefully optimized, that it fit in 64K and did everything needed: navigation, guidance, control, displays, everything. Margaret Hamilton led the software team. She pioneered many of the concepts we now take for granted in software engineering. Error checking, priority scheduling, robust fault tolerance, all of it was invented for Apollo, and the code worked. During the Apollo 11 landing, the computer was overloaded. It was trying to process too much data. Alarms were going off, but the software handled it. It prioritized the critical tasks. It kept running, and Armstrong landed safely. That's incredible software engineering. Even today, with all our tools and techniques, creating software that's reliable is difficult. And they did it in the 1,960 seconds with primitive tools. But here's what I find fascinating. Modern spacecraft computers are much more powerful, much more sophisticated, but they're also more complex, more prone to bugs, more vulnerable to failures. The Apollo guidance computer was simple. It did one thing, and it did it perfectly. Modern computers try to do everything. And sometimes complexity is the enemy of reliability. So in some ways, we've gone backwards. We have more powerful computers, but less reliable ones. We have more features, but more bugs. We've traded simplicity for capability. And that's one reason why it's hard to go back to the moon, because we can't accept the simplicity of the Apollo approach. We want more capability, more redundancy, more safety features, and all of that adds complexity. Now let me talk about the spacesuits. The Apollo A7L spacesuit was a marvel of engineering. It had to maintain pressure about 3.7 pounds per square inch. It had to provide oxygen. It had to remove carbon dioxide. It had to regulate temperature. And it had to be flexible enough to allow the astronauts to move. Think about what's involved here. The pressure inside the suit wants to make it balloon out like an inflated tire. But the astronauts needed to bend their joints, move their fingers, walk around. So the suit had to have special joints, convoluted sections that allowed movement while maintaining pressure. And the cooling system was ingenious. Water-cooled garments worn under the suit, water circulated through tubes, absorbing body heat, then passing through a sublimator that vented the heat into space. Elegant, simple, effective. But here's what's remarkable. They designed these suits in just a few years. They tested them, refined them, and they worked. The astronauts spent hours on the lunar surface in these suits. No failures, no catastrophic leaks, no overheating. Compare that to today. NASA's new spacesuit program has been in development for over a decade and is billions over budget. The suits still aren't ready. And when they are ready, they'll be more complex, more capable, but also heavier and more expensive than the Apollo suits. Why? Because we've added requirements. We want longer mission duration. We want better mobility. We want more sizes to fit different body types. All good things. But all of them add complexity and cost. The Apollo suits were custom made for each astronaut. They fit perfectly. But they were also specialized for moon missions. They wouldn't work as well for Mars or for long-duration spacewalks. So again, we're trading simplicity for versatility. And that makes it harder and more expensive. Now, let me talk about something that really puzzles people. The lunar module. This thing looked like it was made from tin foil and curtain rods. It didn't look like it could fly in Earth's atmosphere, let alone land on the moon. But appearances are deceiving. The lunar module was actually a brilliant piece of engineering. You see, on the moon, there's no atmosphere, no aerodynamics, so the spacecraft doesn't need to be streamlined. It just needs to be functional. And the thin walls, that's because every pound matters. Getting mass to the moon is incredibly expensive in terms of fuel. So they made everything as light as possible. The walls were just thick enough to maintain pressure and provide micrometeorite protection. Nothing more. And you know what? It worked. The lunar module landed 6 times. It took off 6 times. It rendezvoused with the command module 6 times. Perfect record. But here's what's interesting. The descent engine, the rocket that lowered the lunar module to the moon's surface, had never been tested in a full landing profile before Apollo 11. They tested it on Earth, in vacuum chambers, in simulators, but never in actual lunar conditions. So when Armstrong and Aldrin descended to the moon, they were essentially test pilots. They were trying something that had never been done before. And it worked on the first attempt. Now, you might say they were lucky, and maybe they were, but I think it's more than luck. I think it's a testament to the quality of the engineering, the thoroughness of the testing, the skill of the astronauts. But it also shows how much risk they were willing to accept. Today, we would never attempt something like that. We'd want multiple unmanned test landings first. We'd want to prove the system before we put humans on it. And that's another reason why it's hard to go back, because our risk tolerance has changed. We're not willing to accept the same level of danger that they accepted in the 1,960 seconds. Now let me talk about navigation. How do they know where they were? How do they navigate from Earth to the moon with such precision? Well, they used several techniques. First, they had powerful telescopes on Earth tracking the spacecraft. Ground stations could measure the spacecraft's position and velocity by analyzing the radio signals. But they also had onboard navigation. The spacecraft had a sextant, yes, a sextant like sailors used for centuries, adapted for space. The astronauts could sight on stars and use those measurements to calculate their position. And the guidance computer would take all this information, the ground tracking, the sextant measurements, the inertial measurements, and compute the optimal trajectory. It's remarkable when you think about it. They were navigating across 250,000 miles of space with a combination of ancient techniques, the sextant, and cutting-edge technology. And it worked. But here's what fascinates me. The accuracy was extraordinary. They could hit a target on the moon within a few miles. That's like throwing a dart from New York and hitting a bullseye in Los Angeles. The precision required is mind-boggling. And they did it with 1,960 seconds technology, with limited computational power, with techniques that seem almost primitive by today's standards. Today, we have GPS. We have precise atomic clocks. We have powerful computers. Navigation should be easier. And in some ways, it is. But in other ways, we become dependent on these systems. We've lost the ability to navigate using simpler methods. And that's a problem for deep space missions. GPS only works near Earth. Our atomic clocks need to be synchronized with Earth-based systems. If something goes wrong, if we lose contact with Earth, can we still navigate? The Apollo astronauts could. They had backup methods. They could navigate by the stars if necessary. That robustness is something we need to recapture. Now let me talk about life support. Keeping astronauts alive in space is incredibly challenging. You need oxygen. You need to remove carbon dioxide. You need water. You need temperature control. You need waste management. The Apollo spacecraft used chemical systems for most of this. Oxygen was stored in tanks. Carbon dioxide was removed using lithium hydroxide canisters. Water was a byproduct of the fuel cells that generated electricity. It was a consumable system. Use it once and throw it away. Not very efficient, but simple and reliable. Today, the International Space Station uses regenerative systems. It recycles water. It splits water into oxygen and hydrogen. It scrubs and recycles the air. Much more efficient for long-duration missions, but also much more complex, more things to break, more maintenance required. For a moon mission, the Apollo approach was perfect. The missions were short, just a week or so. Consumables worked fine. But for Mars, for longer missions, we need regenerative systems. We can't carry enough consumables for a multi-year mission. So we're developing these systems, testing them on the ISS. But they add complexity. They add mass. They add cost. And that's another reason why going back to the moon is harder. Because we're not just trying to replicate Apollo. We're trying to build systems that will work for longer, more ambitious missions. Now, let me address something that conspiracy theorists love to bring up. The photographic evidence. They say the photos are too perfect, too well composed, too professional. And you know what? They're right about one thing. The photos are remarkably good. Almost every shot is well framed and properly exposed. But here's the explanation. The cameras were specially modified, Hasselblad 500 EL cameras. They had a raso plate, a glass plate with crosshairs etched on it that imprinted a grid on every image. This grid serves two purposes. One, it proves the photos are unaltered. Any editing would distort the grid. Two, it allows scientists to measure distances and sizes in the photos. The cameras had fixed focus set to the hyperfocal distance. So everything from about 10 feet to infinity was in focus. The astronauts didn't have to focus. They just had to point and shoot. The exposure was preset based on the lighting conditions on the moon. The sun, the lunar surface reflectance, it's all very predictable. So they could set the exposure in advance, and it would work for almost every shot. And the composition, the astronauts practiced. They took thousands of practice photos on Earth. They trained until framing a shot became second nature. So the quality of the photos isn't evidence of a hoax. It's evidence of careful preparation and good engineering. But here's what's interesting. We have the original film, the negatives, and they show evidence of being exposed in space, tiny tracks from cosmic ray hits. These are high energy particles that pass through the film and leave traces. You can see them if you look carefully. These cosmic ray tracks are impossible to fake. You can't create them in a lab, at least not convincingly. They're proof that the film was exposed to the radiation environment of space. So the photos are real. They were taken on the moon, and the quality is due to good preparation, not fakery. Now let me talk about something that's often overlooked, the logistics. The sheer scale of the Apollo program. At its peak, 400,000 people were working on Apollo. Contractors, engineers, technicians, administrators, across the entire United States. If the moon landings were faked, all those people would have to be in on the conspiracy. Or at least a large number of them would have to know. And in 50 years, not one person has come forward with credible evidence of a hoax. Think about that. Humans are terrible at keeping secrets, especially big secrets involving lots of people. Someone always talks, someone always leaks. And yet, despite thousands of people working on Apollo, despite 50 years of investigation by skeptics and conspiracy theorists, no one has produced any credible evidence of a hoax. The simplest explanation, it wasn't a hoax. It really happened. But let me address another common claim, the flag waving. I mentioned this earlier, but let me go deeper. In the vacuum of the moon, objects behave differently than on Earth. There's no air resistance. So when you set something in motion, it keeps moving. It oscillates longer. It takes longer to settle. The flag had a horizontal rod at the top to keep it extended. When the astronauts planted the flagpole, they had to twist it and push it into the lunar soil. That twisting created motion in the flag. And because there's no air resistance, the flag kept waving for several seconds. In some of the video footage, you can see the flag moving. But if you watch carefully, you'll notice it only moves when the astronauts are handling the pole. When they step away, the flag continues to move briefly, then stops, exactly as you'd expect in a vacuum. On Earth, in air, the flag would stop moving almost immediately. The air resistance would damp the oscillations. But on the moon, the flag keeps moving That's actually evidence that they were in a vacuum, evidence that they were really on the moon. Now let me talk about the shadows. Another common conspiracy claim is that the shadows in the lunar photos go in different directions, which they say proves multiple light sources, which they say proves studio lighting. But the explanation is simple geometry. The moon's surface isn't flat, it's uneven. There are hills, craters, slopes. When light hits an uneven surface, shadows can appear to go in different directions, even though there's only one light source, the sun. You can test this yourself. Go outside on a sunny day. Look at the shadows on uneven ground. They don't all point in exactly the same direction. That's normal. That's how light and shadows work. So the varying shadows aren't evidence of multiple light sources. They're evidence of an uneven surface, which is exactly what the moon has. Now, let me talk about something really important, the tracking data. During the Apollo missions, radio telescopes around the world tracked the spacecraft. Amateur radio enthusiasts picked up the signals. The Soviet Union monitored everything. These independent observers all confirmed that the signals were coming from the moon. They could tell by the time delay radio signals travel at the speed of light, so there's a 1.3-second delay from the moon. They could tell by the Doppler shift in the signals as the spacecraft moved. You can't fake that. You can't create signals that appear to come from the moon when they're actually coming from Earth. The physics doesn't allow it. So we have independent verification from multiple sources that the Apollo spacecraft went to the moon. Not just NASA saying it, independent observers confirming it. That's pretty strong evidence. Now let me talk about the retroreflectors. During the Apollo missions, astronauts placed laser retroreflectors on the lunar surface. These are special mirrors that reflect light back exactly in the direction it came from. And you know what? You can bounce a laser off these retroreflectors right now. Observatories around the world do it regularly. They measure the distance to the moon with incredible precision by timing how long it takes light to travel to the retroreflector and back. How did those retroreflectors get there? Someone had to place them. And the only missions that went to those locations were the Apollo missions. So we have physical evidence still on the moon, still functional after 50 years, proving that astronauts were there. Now, conspiracy theorists say that unmanned probes could have placed the retroreflectors. And technically, that's true. The Soviet Union did place retroreflectors on the moon using unmanned missions. But if Apollo was faked, why would NASA bother sending unmanned missions to place retroreflectors? That would be almost as hard as sending astronauts. What's the point? The simplest explanation is that astronauts placed them, because astronauts went to the moon. Now let me talk about something that really demonstrates the challenge. The Saturn V rocket. This thing was massive, 363 feet tall, 6.5 million pounds, fully fueled. The largest, most powerful rocket ever built, and it worked. 13 launches, 13 successes, including launching humans to the moon 6 times. But here's what's interesting. We can't build a Saturn V today, not because we don't have the technology, but because we don't have the infrastructure. The factories that built the components have closed. The tooling has been scrapped. The supply chains have disappeared. We could design a new heavy lift rocket, and we are, with the Space Launch System. But it would be different from the Saturn V. It would use different engines, different materials, different techniques. So in a very real sense, the Saturn V is a lost capability. We did something in the 1,960 seconds that we can't easily repeat today. Not because it's impossible, but because we'd have to rebuild an entire industrial infrastructure, and that's expensive, really expensive, which is why we haven't done it. But this also proves that the Saturn V was real, that it flew, that it worked, because we have the hardware, we have the launch pads, we have the documentation, we have the photos and videos of the launches. All of that exists. It's not a hoax, it's history. Now let me talk about Apollo 13. This is actually one of the strongest pieces of evidence that the moon landings were real. Because if you're faking missions, why would you fake a failure? Apollo 13 suffered an explosion in the oxygen tanks. The mission had to be aborted. The astronauts barely made it home alive. It was a near disaster that could have been a tragedy. If NASA was faking the missions, they would have faked a success, not a failure. They wouldn't have risked the negative publicity, the questions, the investigations. But Apollo 13 really happened. The explosion was real, the emergency was real, and the successful return of the astronauts was real. And you know what? The way they solved the problem demonstrates the reality of spaceflight. They had to improvise. They had to use duct tape and cardboard to adapt the air scrubbers. They had to conserve power. They had to manually navigate using the stars and the Earth's horizon. All of those problems and the solutions are completely consistent with real spaceflight. They're the kinds of challenges you'd face in space. And the solutions are the kinds of clever improvisations that real engineers and astronauts would come up with. You can't fake that level of detail. You can't script those kinds of realistic problems and solutions. They had to be real. So Apollo 13 actually proves that the moon missions were real, because a hoax wouldn't include a near fatal failure. Now, let me address the radiation question one more time, because it's really important. A lot of people focus on the Van Allen belts, but the Apollo spacecraft passed through the belts quickly in about an hour. And they passed through the thinner regions of the belts, not the most intense parts. The total radiation dose the astronauts received from the Van Allen belts was relatively small. Estimates range from 1 to 10 rem, depending on the mission. That's comparable to a few years of natural background radiation on Earth. Not safe, certainly, not something you'd want to do repeatedly, but survivable. And in fact, the astronauts did survive. They didn't suffer radiation sickness. They didn't die young from cancer at higher rates than the general population. So the radiation was a risk, but it was a manageable risk. And they managed it. But here's what's interesting. Modern spacecraft would use different trajectories. They'd spend less time in the belts. They'd use better shielding. They'd have better radiation monitoring. Not because it's impossible to transit the Van Allen belts, but because we can do it safer now. We don't have to accept the same level of risk. And that's another reason why it's harder to go back, because we're not willing to cut corners the way they did in the 1,960 seconds. Now let me talk about the lunar samples. 842 pounds of rocks and soil. These samples have been studied by scientists all over the world. Thousands of scientific papers have been published based on these samples. And the samples tell a consistent story. They're from the moon. They formed in the absence of water and atmosphere. They're ancient, billions of years old. They've been bombarded by micrometeorites and solar wind. All of this is exactly what we'd expect from the moon. And it's impossible to fake. We don't have the technology to create fake lunar rocks that would fool every scientist who studied them for 50 years. So the rocks are real. They came from the moon. And the only way to get them was to go there. But here's what really convinces me. The samples from different Apollo missions are different. The rocks from the highlands are different from the rocks from the Maria. The soil composition varies from site to site. If you were faking samples, you'd probably make them all similar. But the real samples show the geological diversity of the moon. Different regions have different compositions, different ages, different histories. That level of detail is impossible to fake. You'd have to know in advance what each region of the moon was like. And we didn't know that before Apollo. We learned it from Apollo. So the diversity of the samples proves they're real. That's why the moon landings matter. Not because we planted a flag 50 years ago, but because they showed us what's possible. They proved that space is hard, but not impossible. Difficult, but achievable. And now it's up to us, to this generation and the next, to build on that legacy. To not let another 50 years pass without progress. To keep pushing forward, because the universe is waiting. The future is calling. And humanity's destiny is among the stars. So when people ask me, was it impossible for humans to land on the moon? I tell them this: yes, it was impossible. By any reasonable measure, it should have been impossible. But